to assign somebody on your team to be a project manager. That way, instead of several people all emailing at once, everything can kind of go through one person. That's how it generally works. If somebody gets assigned as a project manager, you guys can choose whoever that is on your team to basically handle any administrative stuff. You guys can, of course, help out, but that person is going to be ultimately responsible for primary communication with me. Make sense? All right. Are there any questions about the project? One clarification, actually, on problem 2 of homework 5. I accidentally indicated bending moment, which is stupid because the entire bending moment is literally, it's undergoing pure bending. So it should be determine the maximum bending stress, not the bending moment, and its location. So that's an important clarification that needs to be made. This is my favorite chapter. I'm excited for today. And I like how it actually says Mech 363 here. I did upload the PowerPoint slide, I think. Does everyone have access to the PowerPoint? Yep. All right. I also added technically an extra example, which is probably beyond the scope of this class, but I wanted you guys to see how something a little bit more complicated with frames gets analyzed. It's basically a very similar procedure to beams, but it becomes a nightmare once you're dealing with more two-dimensional structures instead of just 1D beams. All right. So today we are going over the analysis and design of beams for bending. More specifically, beams that aren't necessarily directly exposed to pure bending. All of chapter 4 was associated with pure bending. What is pure bending? That is when a structure is explicitly subjected to some type of rotational force like bending moments. But beams, on the other hand, will be exposed to distributed loads, point loads, or some variation thereof, some type of point moments, for example, which can impose both shear forces and bending moments onto structures. In the case of frames, you can have shear, bending moments, and axial forces all contributing to loading of an interior structure. So for example here, for a concentrated load such as the beam, there's going to be a point load. So anybody want to take a guess at where they think the maximum bending moment would be? Where do you think the maximum load is going to occur? At the point force in terms of bending. What about the shear force?
Would it be like along like the cross section that point force is at?
The shear force, if that point load is actually directly at the center, is actually felt the entire length of the beam. All right, we'll get into a little bit about the shear force diagrams and internal forces, but this is going to involve a lot of cutting sections and analyzing the internal forces. Remember when we were doing that with axial loads and analyzing compression and tension? It's the same thing as here, but I'm gonna be doing some variation in how the textbook does it because I have my own unique way that I like to teach it. It's the way that I taught it, and it helps with more complicated structures in general. So for right now, we're going to be just primarily dealing with statically determinate structures. So that's, again, point load, distributed load subjected to with pins and rollers on the left or cantilever beams on the right. We're not going to focus too much on statically indeterminate structures right now. We'll eventually get to it once we get to chapter 9. If you guys remember, to solve a statically indeterminate structure, you need compatibility. And compatibility tells us that we can basically determine unknown reaction forces or redundant reaction forces by knowing how it deforms. So before we can technically solve statically indeterminate systems, we need to know how statically determinate systems deform, which that's going to be in another few weeks, so don't worry about that right now. All right, so we have different types of loads, including transverse loads. Here, in this case, what you guys might have seen, which we saw this previously, let's say that P1 and P2 equal each other, right, then one thing that you guys would likely notice is that in this case, B and C would be subjected to pure bending. However, when they're not equally to each other, it's not pure bending. It's actually a combination of bending moment and shear forces, which complicates the problems a bit. We can still handle it, but it's not like the stuff that you would see in chapter 4 where we had pure bending and you're just given a moment. So this is basically going to show you guys how to obtain those internal moments from analysis. All right. Other than concentrated loads, we can have distributed loads. Again, the loads are ultimately going to affect the internal forces of the structure. A nice way to think about it is if you have 10 pounds of point load directly at the center of the beam does not equal 1 pound per foot on a 10-foot long element. Yes, it's the same amount of load and it'll be exactly the same for external equilibrium, but internal equilibrium, the behavior is actually entirely different. So when it comes to internal forces, again, we cut sections, and if you guys look at the bottom there, we have internal sign conventions for shear and moment. What I'm actually going to do is just kind of delete that, and basically what I want to show you guys is the methodology that I kind of learned to really figure out all of this. So let's say that we had that beam that was on the previous page. Let's say that's the beam, all right? What I personally like to do is I'll draw what's called a reference fiber. So let me actually just delete that really quick. Let me just like probably make this a bit easier. That's not working, come on. So let's say that we had a beam here. All right, you've got a pin here and a roller here. And it's subjected to some forces or whatever the hell. All right, doesn't really matter what the forces are. From what the textbook will show you is from this sign convention, this is generally considered in industry as the positive sign convention. So any textbook solutions, if you guys are looking at homework problems, you guys will always see those section cuts being taken with respect to the right-hand side, with the shear moving vertically downwards and moments moving counterclockwise. Moments are positive that way because of the right-hand rule, but shear is positive moving downwards because we assume that the beam under most loading cases is technically moving vertically downwards. So in a lot of cases when you're designing with beams, vertical displacement downward is actually positive, not negative. Here, what I want to show you guys though is a different kind of methodology to, I guess, dealing with these types of problems. Let's say here that we had the beam and we cut a section here. Come on, whatever. And let's say that it's subjected to some type of loading or whatever. You know, you would have your reaction force, R, we'll call that W. When you cut a section through here, what I personally like to do is I like to draw a little reference fiber here, all right, which is basically just going to be the side that we're using for our sign convention. And from here, what I'll do is assign a shear force, not necessarily enforcing vertical downwards movement, but indicating that the shear force is going towards the reference fiber. And then from here, we would apply a moment such that that reference fiber would get placed in tension. And that would be the positive sign convention. Now, what if instead I wanted to analyze the forces on the left-hand side? All right, so let's say that we cut a section right through here, and this was the point load, and this was like some other reaction. We'll call this R2, and we'll call this like P, WP. Then we can draw a reference fiber here, but on the left-hand side, positive shear would be moving away from the reference fiber. And then the moment would still be going in such a way that it causes tension. Now, does the reference fiber need to be directly on the bottom? No, you can assign the reference fiber however you want, but then you need to follow the sign convention rules that we just discussed. So, for example, if instead I wanted to, let's say, assign the reference fiber up here, then technically what we should be doing is applying a counterclockwise moment, M, such that the reference fiber is in tension, and then a shear force, V, where the force is going towards the reference fiber. And that would be the positive sign convention for that reference fiber. And then the exact same thing for the opposite side, where if we applied a reference fiber just right here, then moment would get flipped and the shear force would go away. So whenever you're taking cuts and analyzing the internal forces on the left of the cut, basically everything is kind of opposite to the positive sign convention. Now, why do we do this? Why is that reference fiber important? Well, the reason being is it negates everything. So if you think about it, if you were to analyze the internal forces here with the reference fiber on the bottom, and then analyze the internal forces with the reference fiber on the top, you'll get the same magnitude, but equal and opposite in sign. A good way to think of it is if you're getting the bottom to be positive, indicating its intention for the bending moment, and then you get it for negative here, then the top indicates it's in compression. It can be very confusing at times. So worst case, if you guys really hate using the sign convention, then my recommendation is just always cut it on the right-hand side and just use that default sign convention. That's something that's very commonly used in industry. The reason why I'm telling you guys about this reference fiber stuff is because for most numerical software that you guys see, they use local and global coordinate axes in order to clarify positive and negative shear. And so the magnitude of those forces is heavily dependent on how the coordinates are defined in software. So just because you get a negative bending moment does not mean it's bending a certain way. You need to look at the coordinates and be able to interpret your results. I know it can get a bit confusing. We'll work on examples later on. All right, so just as a reminder, there's different types of supports. You can have a simply supported beam. This is just a pin and roller connection. You can have overhanging sections of said simply supported beams. You can have cantilever beams. And then once you start getting into the realm of statically indeterminate structures, you'll have continuous beams. You can have beams that are fixed on one end and a roller on the other, fixed on both ends. In some complicated scenarios, you can have case A, where you may have a fixed end, a hinge, and then a roller. That would actually be a statically determinate system. So here, this is technically statically determinate. And then the same thing here with the pin and two rollers. Because of the fact that you have a hinge, it's also statically determinate. Does everyone understand why? No. Why? Oh, no. Oh, you. The reason being is because you can split the structure at the hinge and then basically separate it to two beams. So you can separate section A into beam AH and then beam HB. And then you can solve for the pin forces, because the pin forces are going to be the same in both sections of the structure. The force is transferred. So because of that, you can actually solve those relatively complicated structures using hinges. Have you guys worked with hinges before in statics? No? You guys haven't seen really frames or anything like that? Did you guys see frames in statics?
Yeah.
You guys did? And you guys didn't deal with hinges at all, with complicated structures? Oh, this is going to be a fun semester because I'm going to be doing that. All right. So I think just getting straight into the thick of what we're trying to get to, I just want to give you guys a straight up example. All right. So I want you guys to sketch the internal force diagrams and then compute the maximum normal stresses. All right. So first step of any single one of these problems is to conduct external equilibrium. It's almost going to be nearly the same exact steps as axial loads. All right. So what type of reaction forces are the fixed end subjected to? Ryan, you said something.
It's all three. It's y, x, and moment.
Exactly. Are there any x forces though?
No.
No, so we'll say that the x force is just 0. What about the y force? What's the vertical reaction?
Equal and opposite.
Yeah, so the reaction force here is just F. What about the moment though?
L times F.
L times F. It's going to be positive L times F because of the fact that that force, the externally applied force over on the free end, would be causing a negative moment. So that to counter it, the reaction force has to provide a positive moment. Does that make sense? Great. Now, the next step to solving these problems, cut a section, all right? In this case, let's just cut a section right through here, and we'll call this section A. All right? Now, just to simplify things, I'll just zoom in here. Never mind, actually, I'll redraw it. All right, so 2 is internal equilibrium. I will do internal equilibrium in blue. All right, so we've got the fixed end here. This is the line, and that's our section, A. Our externally applied forces are FL and then F. All right. Now, let's assign a reference fiber. What do you guys want to look at? Top or bottom of the beam? Let's just look at the bottom for now. So we'll say that the reference fiber is at the bottom, and the length of this section we'll call X. It's some arbitrary dimension. All right? Now, if we assign the reference fiber to the bottom of the beam, what does the internal force diagram need to look like? Not the internal force diagram, the internal forces. How are they drawn? Look back at how we sketched up the diagrams previously. Yeah?
It should be going down and the moment going counterclockwise.
Oh, wow, that's thick. Yeah. Shear is vertically downwards, and then the moment is clockwise. Counterclockwise, sorry. You were right. All right. Now, what we need to do is take equilibrium of this body here. All right? So, we could do sum of the forces in y, set that equal to 0. What do we get? What's our equation look like?
F equals V.
Yes. So our negative v plus f, which indicates that our shear force, we'll call it v of x, is equal to f. Now we need sum of the moments. But where do we take the moment about? Here's the fun part. When you're analyzing these, you can ignore that little figure right there and now treat this as if it's a cantilever beam, where the cut section is your fixed end, right? Because if you think about it, it's basically just a fixed end. So we could take a moment about the cut. What we'll get is m. Oh, sorry. This should be f. And then somebody finish the equation for me. We've got our internal bending moment of m. What else?
FL.
Positive or negative?
Positive.
And then what else? Yeah. So that means we can rewrite the bending moment as F times X minus L. Any questions so far? So what does this tell us? It tells us that if we were to plug in, let's say, x equals 0. So x is basically, x equals 0 is directly at the free end. What would we get for the bending moment? Negative FL. Now we can take that negative sign and determine if our reference fiber is in tension or compression. What do you think?
It would be compression since it's negative.
Exactly. They don't teach you that generally in this class, but that's a good way of knowing if it's positive or negative. Matter of fact, if we had placed the reference fiber on the top and used the appropriate sign conventions that I had showed you guys for the reference fiber, we would actually get m naught equal to positive F times L. So we would get the same magnitude of bending moment, but it would just indicate that the top, which is our reference fiber, is in tension. So it's the same answer, basically. It's just a matter of what coordinate system you're looking at. All right. Now, x equals L. I think it's pretty self-explanatory to see that the bending moment would just be 0. So, let's copy and paste this really quickly. And now what we do is we draw our internal force diagrams. Right? I personally like to draw them really neat. So that's going to be for shear. This is going to be for moment. We know that our shear force is constant F along the entire length. So F, and then it closes out. and that shear force is F. So this is a state of pure shear. Now for bending, on the other hand, at the initial position, it's negative F times L. So it goes down, negative FL. And then we notice that from M of X, it's a linearly decreasing bending moment. So our internal diagram closes out to 0, where M of X is equal to F times X minus L. And then from here, if you wanted to, you can find what the maximum bending stress is using my over I. For a rectangular cross-section, we can actually simplify this to just be m over s, where s is just equal to bh squared over 6, which means that our bending stress is just 6m over bh squared. But here's the thing, all right? If we wanted to find the maximum bending stress, what's the moment that we would plug in? Negative FL, right? So sigma max is just equal to negative FL times 6 over BH squared. Or if you wanted to express it in terms of sigma x and plot the stress, just plug in the entire function and then you can set iterations for differing values of x. This is if you wanted to plot the shear and moment diagrams as functions of x in like MATLAB or Excel. This especially becomes helpful if you have like b or h varying as a function of x, because then you can really see how it varies. Any questions? All right. Here's another example. All right. The force is directly in the middle at midspan. So let's first conduct external equilibrium. Simply enough, it's just going to be F over 2 and F over 2 on both sides. Next, we conduct internal equilibrium. All right. So let's look at our diagrams really quickly. We need to cut a section. So let's call this section AA. But what you'll notice is that there's technically going to be two parts. All right, there's a discontinuity in the load because of the fact that you have point load. So you're actually going to need to cut two sections because you'll have two internal force components. So if we let this equal to A, this reaction is F over 2, and this dimension we will call X1. Let's again say that the bottom here is the reference fiber, such that V is moving vertically downwards and M is anti-clockwise. We can sketch the internal shear and moment equations. So from sum of the forces in Y equals 0, what do we get for our equation? Exactly. Which tells us that the shear force because of the fact that the load is applied at midspan, the shear force is about half the load. So when you're designing the beam, you only need to design for a shear force of half of F, all right? You wouldn't believe how many times I have COT students trying to tell me that just trying to plug in F, I'm like, you're doubling the load that's really required. From here, take moment about the cut again, and I'll just do it really quickly. We'll get M minus F over 2 times X, which means that we get an M of X, 1, I'll say, equal to F times X1 divided by 2. Keep in mind that X1 is within 0 and L over 2. Now let's continue over to the second equation. And what we'll see is again F over 2, yikes. The point load F, and then this is our section B. This becomes L over 2, and then this becomes X2. Again, we'll just say our reference fiber is on the bottom. Shear force, bending moment. Do sum of the forces in Y equals 0, and we'll get F over 2 minus F minus V, and we'll actually get that the shear force is equal to negative F over 2. Notice how it's negative now and not positive. So this is important to note. This is why we need to cut that second section. This will actually tell us, interestingly enough, that the beam will actually have a tendency to kind of move upwards from that point. It's weird to think about, but imagine as if the beam was vertically loaded downwards like that. You can see the beam is tending to go downwards. And then from that point going to the right, it's going upwards. Again, negative positive shear is indicating downwards movement. So because it's negative, the beam is trying to go back up now. From the moment about the cut equals 0, we're going to get M plus F times X2 minus F over 2 times L over 2 plus X2. All right, simplify this. M is equal to FL over 4 minus Fx2 over 2 plus Fx2. Is that right? No. That should be plus and then minus, which means that our bending moment of x2 is equal to FL over 4 minus Fx2 over 2. Where again, 0 is less than or equal to x2, which is less than or equal to L over 2. Last step, just draw the shear and moment diagrams. So let me just erase all of this. I wish it was an easier way than just having to use the erase tool. All right, so we'll use this for our shear force diagram, and this here for our moment diagram. All right, shear force. we got that it was positive V F over 2 for section A. Oh, what happened? There we go. And then we got that it was negative F over 2 in section B. For the bending moment, what do we notice? For all values of x1, it's positive, the bending moment, which indicates that the bottom reference fiber is in tension. And then for x2, for all values of x2, it's still technically positive because we have a y-intercept of FL over 4. It's just that this time, the bending moment decreases as we go to the right. So, our bending moment will look kind of like this, if it wants to draw properly. And that's how the beam looks, the bending moment diagram. And then similarly, if you wanted to compute the maximum stress, you would need to know what the section modulus is, or you can use the y over I equation, but I think we can kind of skip that step. Hopefully you guys know how to do that. Yeah, and then this would obviously just be the maximum bending moment. Any questions about this? About this example? They get much more complicated. For example, in example 3, now we have a distributed load. All right? It's not as bad as you think. All right? First, we need external equilibrium, right? What is our external equilibrium going to be? We're going to have a by, and then a moment. And notice how the coordinate is taken with respect to the left. That's just a problem-defined thing. You guys can obviously assign coordinates however you want when you're in practice. This example is just calling out for the coordinate from the left-hand side. So pay close attention to that end times. What's BY and what's MB? Yeah.
Would BY be like W times L, since it's like the whole distribution over the length?
Exactly. But what about MB? You guys did see distributed loads, right, in statics?
Statics was a year ago.
A year ago? What? No, say what you're going to say. Come on. Travis.
Is it the weight integrated over the length from 0 to L?
Yes, that's the force, which would give you W times L.
And then
Where's all of this load technically acting? Where would it be concentrated? It's a rectangle.
Give me right at the center.
Yeah, so it would be WL times L over 2. So your bending moment would be WL squared. All right? But if you write out the equilibrium equation, if you assume a positive sign convention, you'll get that this has to be negative WL squared divided by 2, which means it's technically acting clockwise. Does that make sense? That's what I mean. All right, so that's external equilibrium. Now for internal equilibrium. All right, one thing that's nice about this problem, and most times with distributed loads, is that they're continuously loaded. All right, which means that there's no immediate discontinuity, which means we can actually express the shear and moment diagrams all as one expression. If I had a point load here, you would need to break up the shear and moment diagrams accordingly. But because it's just a distributed load, it's nice and simple. So let's cut a section. Let's say just right here, A. And then we draw the distributed load as such with a coordinate of x. All right. Now, what do you guys want to do for the reference fiber? Top or bottom? You want to do top this time? Let's do top this time. Which means that for our sign convention, shear should move upwards, and then the bending moment should cause it to be in tension. All right, so do sum of the forces in y equals 0. This is going to be negative W times X plus V, which means that our shear force is equal to W times X. Positive.
Why do you keep writing V of X or Vx? I missed that.
Sorry, it's this should all just be a function. So all of this is technically functions thereof. M of x, V of x. Yeah, all of it should be functions. Primarily because in some instances, like the shear force, previously we had saw that it was just point loads, so the shear force didn't really matter. It was just a constant value, but the bending moment was a function of x. When you're dealing with distributed loads and higher magnitudes of x to the n or whatever, then it becomes more of a function, the shear and moments. So if I just write v or v of x, they're synonymous to each other. That's what I'm trying to get to. All right. Now, take a moment about the cut, set that equal to 0. What we get is negative m of x plus W x times x divided by 2. And what we get is m of x is equal to wx squared divided by 2. The bending moment is positive, which means our reference fiber, the top, is in tension. And then wx is just positive from the math. Anybody notice anything about v of x and m of x? We actually get into a little bit of it next lecture, but I just want to see if anybody notices that, the relationship right now. Yeah,
Constant integral of unit.
exactly. So, what you guys should hopefully notice is that m of x is equal to the integral of v of x dx. More traditionally, it's generally written that v of x is equal to dm of x over dx, but what does this basically mean? It means that the bending moment is just equal to the area under the shear force diagram. One nice way to think about it, for example, let's take a look at this diagram here. All right. What is the horizontal length of each of these rectangles? It's just L over 2, right? So F over 2 times L over 2 is the area of this full rectangle here. Guess what? Equals FL divided by 4 when you multiply the two. Let's say we wanted to find the bending moment here at that point. Well, then you would just take the area bounded within that region. So if that was L over 4, then the bending moment would technically be FL over 8. Do you guys see that? Now a little bit trickier. Let's say we wanted to take the bending moment on the right-hand side. What you need to do is take the area of everything from the very far left-hand side all the way to the point of interest. So it's not just a matter of just taking this area. You would need to take all of that area also. So those two areas multiplied together and summed up would give you technically FL over 8 also, which is basically the same as this area under here. Make sense? We'll get into a little bit more solving problems that way. Right now, I just want you guys to be very comfortable with cutting sections in the force body diagrams into the structures and then drawing the force body diagrams that way, because it becomes very important later on. All right. Now, if we wanted to draw the shear and moment diagrams for this problem specifically, let me just erase all of this again. Da-da-doo. So V of x, M of x. We look at the shear force. V of x is going to range linearly from x equals 0, so the shear would be 0. And then at x equals L, the shear force is just W times L. So our shear force, in this case, is WL. And that's assuming that this is our reference fiber. The bending moment varies quadratically, Wx squared over 2, which means that our bending moment is going to be quadratic, up to WL squared over 2. Now, if we had used the sign convention that we had previously dealt with, where the reference fiber was on the bottom, then our diagrams would basically just be negative and negative. So it would be the same equations, just everything is negated. Are there any questions about this so far? Nothing? Good, because the next one is it's a fun one. Triangles. I hate these because they're annoying. But wait till you guys see the integral problems. I will not be doing that one. That's why I took it out of the PowerPoint. I don't even know if it's on the Brightspace one, but there's problems in your beer textbooks. All right. So, how would we solve for this? First step, again, external equilibrium. MB, RB, or BY, I'll say. What is BY and MB equal to? Yeah.
BY would be 1/2 W naught times L. And then MB would be the W 1/2 W naught times L, but then isn't it times 1/3 of L?
Yeah.
Like 50%.
Which equates to W naught L squared? Over 6. Yes. All right. And this is obviously going to be negative because of equilibrium. It's going to have to be negative. All right. Now, the fun part again. Cut sections. This is a continuous function, so because of that, we could just cut one section, AA. For this case, I'll use the reference fiber on the bottom. So our shear force goes downwards towards the fiber, and our bending moment causes the fiber to be in tension. And then we draw our applied load. But here's the thing. What is the magnitude, the peak of this triangular load here? Any guesses? I'll give you a hint. It's nice and simple, and it's already written on here because of the fact that our x-coordinate is taken from the left. If it was taken from the right, it would be a much harder, more challenging thing because then your diagram would technically be a trapezoid.
Is it W?
Not W. It would be W naught times x over L. You guys notice the WX equation? If you had taken x from the right-hand side, you would technically have W naught as the maximum, but then you would also have a minimum point of, I don't think it's W naught x over L. You would have to do the derivation and manually calculate it. It becomes a nightmare. All right, so sum of the forces in the y direction equals 0. Also remember V of x and M of x, not just V and M. V of x is moving downwards, so negative V of x minus the area of this diagram is just 1/2 times W naught x over L times x. Did this screen turn off?
Yeah.
I don't know what's going on with it. Weird. Which means that our V of x is equal to negative W naught x squared divided by 2L. Now we can do some of the moments about the cut, but anybody want to take a guess at what the bending moment is going to be?
Negative W naught x cubed over 6L.
Exactly. Now the reason you don't need to add plus c is because we already have bounds at which x is going to be provided. So it's already it's a definitive integral. All right? And what you'll notice is that the bending moment when x equals L basically equals the reaction moment, negative W naught L squared over 6. So the L in the numerator and denominator cancel out, leaving L squared left on the numerator. Now, to draw it. Erase all of this. Shear force was quadratic negatively, so V of x is equal to negative W naught x squared over 2L, which when you plug in L in the for x, you should get that the peak here is W naught L over 2, which is our reaction force vertically. This is way too low, so let me move that up. And then for our bending moment, it's cubic. Cubic negative. Well, yikes. Where the peak was W naught L squared over 6. Negative. If you guys are using like computers to analyze it, the diagrams would look a lot neater, but hopefully you guys get the idea. Like, I mean, we're all just kind of rough sketching it, so if there's ever times where, you know, you have to draw out a quadratic shear force and then a cubic bending moment, just write the equations next to it so that way the person who looks over your calcs knows, like, okay, it's a cubic function, it's a quadratic function, so on. I don't think we're going to have time to get to this beast, but this problem here, now we want to sketch the internal force diagrams for this as well. We're taking x from the left-hand side, so I'll give you guys just a quick minute to tell me and calculate those reaction forces. Once you got the reaction forces, let me know. Because I cannot proceed without them, because I don't know them. You got it?
Yeah.
All right, what is it?
AY is equal to negative 0.5 newtons and CY is equal to 1.5 newtons.
All right, so technically, everyone gets this? Awesome. Now, looking at this structure, how many sections do you think we'll need to cut?
3.
Yeah. AB, BC, and CD, because there's 3 discontinuities. All right, so let's analyze AB first, where here we just have a 0.5 Newton force. Now we want, whenever we're analyzing our members, we generally want to try and keep consistency with our reference fibers. So for this case, we'll just universally assign the reference fiber to be at the bottom. So V again is going downwards, M is going counterclockwise. And from this, we can do some of the forces in Y, some of the moments about the cut. We will get negative V minus 0.5 newtons. So V of X is constant at 0.5 newtons. And with this M, this distance here is x1. So M plus 0.5 x1. So M of X is equal to negative 0.5 x1. And this is going to be in Newton meters. Now, for the second section, we go through BC. So we'll have a 1 Newton force, the 0.5 newtons acting downwards here. This dimension here was 1 meter, and then this dimension is our x2. Again, we want to keep consistency with our reference fibers. So we have V, M, sum of the forces in Y equals 0, equals negative V minus 0.5 newtons minus 1 Newton. So our shear force as a function of X is just going to be negative 1.5 newtons. Now do some of the moments about the cut. And we get M, minus 1 Newton times x2. So that's just going to be x2. Or plus, technically, because it's a clockwise moment. Counterclockwise, sorry. Plus 0.5 times 1 plus x2. So our bending moment is equal to, let's see, this is going to be negative 0.5 minus 1.5 x2. Am I right with that? 0.5 times x2 plus 1 x2 is just 1.5 x2 plus 0.5. Negate everything. So yeah, should be that. And this is m of x2. That should be x1, x1, v of x2, x2. We just erase all of this. Lastly, do our third cut. Add 0.5 newtons, 1 newton, then 1.5 newtons. This is 1 meter, 1 meter, and then x3. We have V, M. This is our reference fiber. And then we do sum of the forces and sum of the moments. Forces in Y equals 0, negative 0.5 minus 1 plus 1.5 minus V. This gives us a shear force, Vx3, of 0. And then we do sum of the moments about the cut equals 0. Which should be 0.5 times 1 plus 1 plus x3 plus 1 Newton times 1 plus x3 minus 1.5 times x3 plus m of x3. Which I'll give you a hint. M of x3 just equals, I believe it's 2 Newton meters. Or is it negative 2? Let's see, 1, 0.5, 1, 2. Yeah, because if x3 equals 1, then it's 0.5, 1, 2, 3, so that's 1.5. Somebody do the math, let me check. I'm pretty sure it's either positive 2 or negative 2. I'm trying to do the math in my head. And I'm too lazy to. Plus 1, plus 1, times 1. Negative 2? You get negative 2? Okay. So yeah, that makes sense. Which means that the bending moment is actually constant. Which I guess kind of makes sense since it's there's a pure bending point directly at that point. So now we just draw the diagram. Shear force, bending moment. Our shear force for A to B was negative 0.5 newtons. So negative 0.5. Then from B to C was negative 1.5. And then jumped up to 0. And then for bending, the entire thing was undergoing negative bending. So negative 0.5 times x1, meaning that the bending moment varied linearly. And then, let me resketch this slightly. And then it was negative 0.5 minus 1.5 x2, which means it decreased linearly but at a greater slope. And then it was constant. So the bending moment here is negative 0.5. And then the bending moment here is negative 2. That's V of x and M of x. Any questions? As much as I would love to go into the frame analysis, I think I will jump into that next class because it is about 3 pages worth of work. So it takes some time. So I think we'll leave it here. So I'll just stop the recording here. Have a nice week. Project team names. Actually, unless you want to create them now, then we could just throw them on there. And then we could just work on it from there. I don't know. What do you guys want to do? Just the team names as team 1, 2, 3, or you guys want to try and get a little creative? I'll give you guys a few minutes to discuss it.